Hello everybody. The speaker of our seminar today is Professor Giles Gardam from University of Bonn. He shall speak about the famous Kaplansky conjecture. That's the interesting note for people in algebra, but also in geometry. That is why I wrote an email to him last year and asked him about the Kaplansky conjectures. And he kindly agreed to give a lecture about the Kaplansky conjecture on our seminar today. So please, Giles.
Okay, great. Thanks very much for the invitation and the introduction. So I'll talk about the Kaplansky conjectures. These are conjectures
Could you speak a little bit louder?
I'll talk about the Kaplansky conjectures, which are some conjectures for group rings or group algebras. And please interrupt me with questions at any point. So I'm deliberately giving a handwritten talk so that it's easier to be spontaneous in what I explain, rather than just sort of go through the slides. So please, I'm very happy for this to be as interactive as you want. And if there's a million questions and we don't get to the end, that's totally fine as well. Okay, so just to set some notation and definitions, we'll let G be a group. That will be the case throughout. So let G be a group, and we'll let K be any field. So the object that I'm interested in is the group ring KG, or sometimes called the group algebra. So this is one of, I think, two definitions that are going to be important in this talk. So, so the group ring KG. So notationally, I guess this sort of looks something like polynomials, where instead of having some variable t, we have elements of g, and that's really sort of how it behaves. So, what is this ring that I build from a group and a field? It's at least the additive structure is that it's the K vector space with basis G. Right. So in other words, we have finite formal K-linear sums of the group elements, and that's the additive structure on this ring, and the multiplicative structure just comes from the multiplication law on the group and multiplication in the field, and then we extend linearly. So it's the K vector space on basis G with multiplication extending the group product linearly. So, what does this mean? If I take one expression, say sum over elements G in the group of some coefficient lambda sub G times G, and I multiply it by some similar thing, say with coefficients mu, then the resulting thing is just the sum over all pairs of the product of the coefficients in the field times product of the group elements evaluated in the group. Right, so here, of course, the lambda G are these field coefficients. Okay, so the mu H and the G and H are the elements of the group that we're summing over. The running variables in the sums. Okay, so this is something that is probably familiar to a lot of people, and it's a quite basic construction that shows up all over the place in algebra and topology and representation theory. And the reason that this is something natural to consider is something that actually is, I guess, a point of view or a perspective that goes back to Emmy Noether. So representations of my group on K vector spaces are the same thing as modules over this ring. So if we believe that a natural way to try and study a group is to study its representations, we're sort of led in one way or another to wonder about modules over the group ring. So I work in geometric group theory, and among other things, that means I'm really just interested in infinite groups for the most part. And so, my first example is not going to be with a finite group, it'll be with an infinite group. And this will be a very instructive example for what I want to say today, even if it's a very easy example. And that's if my group G is the group of integers, which I will write in multiplicative notation rather than additive notation. So I'll think of this as being generated by some letter t. So these are positive and negative powers of t. In this case, then the group ring I have is something very familiar, right? This is now finite formal sums of positive and negative powers of t multiplied by these field coefficients. And that's just the same thing as the ring of Laurent polynomials. Okay, so just like the normal polynomial ring, but we also have the t inverse there. And of course, the ring of Laurent polynomials is a very nice ring from a ring theoretic point of view. For example, it's a commutative ring and it's Noetherian. And those sorts of properties certainly won't be true for a group ring in general. Like, unless the group itself is abelian, then the group ring won't be commutative. And there's sort of a conjectural picture, but basically the group ring is almost never going to be Noetherian. But there are certain very nice properties that the ring of Laurent polynomials happens to have that maybe all group rings happen to have, at least under some mild assumptions. And so these are a bunch of first order statements about the group ring. So we're not talking about like the ideals, which is something higher order. We're just talking about elements, specifically about things like units, zero divisors, and idempotents. So these are the, oops, sorry, lost myself. Okay, so these are now the conjectures that I'm interested in. I generally refer to them as the Kaplansky conjectures. Actually, the first two of them were, as far as I know, first formulated by Graham Hickman in his PhD thesis. But it was certainly Kaplansky who popularized these conjectures in a series of talks and papers starting in the 50s. Okay, so we have one mild assumption on the group, namely that the group has to be torsion-free. So there's no non-trivial element of finite order. There aren't any non-trivial finite subgroups of G. Okay, so for me, as someone interested in infinite groups, this is a fairly mild restriction. So for example, fundamental groups of aspherical manifolds are always torsion-free. Or if we take some group of matrices over the complex numbers, then if it's finitely generated, it will at least be torsion-free up to passing to a finite index subgroup. So within some sort of finite error, those matrix groups over C will also be torsion-free. So morally, this is close to saying all infinite groups, at least from my point of view. So the conjectures say, provided the group's torsion-free, then KG has first no non-trivial units. Right, so a unit will just be it's of course something that's just invertible on both the left and the right. So if I have some element X in the group ring, for which there exists a Y, that's its multiplicative inverse. So if X is a unit, Well, there are always lots of units in the group ring because every element of the group is itself then when thought of as an element of the group ring a unit. Okay, so I guess formally it's like 1 times the group element. That's always a unit. And of course, any element of the field, then it also gives me a unit, just element of the field times the identity from the group. So there's tons of units, but these are so-called trivial units. And the conjecture says those are the only units we have. So if I have a unit X, then actually it has to be of the form K times G, where K is some non-zero element of the field and G is some element of the group. So that's the first conjecture. The only units we have are the trivial ones. So the next conjecture is that, again, under the assumption G is torsion-free, that there are also no non-zero zero divisors. Okay, so to unpack exactly what this is saying, if I have 2 elements and their product is 0, then at least one of those 2 elements has to be 0 itself. And of course, having 0 divisors is some sort of pathology that we'd like to avoid. And I guess maybe we'd really like to be able to embed our group ring into a skew field. That's sort of very convenient algebraically if we can do it, but certainly we have 0 divisors and that will obstruct the existence of an embedding into a skew field. And finally, there should be no non-trivial idempotents. And idempotent is just something that's equal to its own square. And we should only have the 2 trivial solutions to this equation that we all learned in school. So if something is an idempotent, it should just be 0 or 1. Okay, so those are the 3 Kaplansky conjectures for torsion-free groups. And then on top of that, there's a bonus 4th conjecture, which actually is making a statement about all groups, not just all torsion-free groups. So that then says, finally, that for any G, possibly with torsion, for this conjecture, it doesn't matter. The group ring KG should be what's called directly finite. It's a bit of a funny name to do with decompositions of modules. Maybe I won't get into where exactly the name comes from. It just means something very simple, namely that every left invertible element is right invertible. So in other words, if a product xy is 1, then the product the other way around yx is also 1. Right, so this is also called von Neumann finite, among other things. Okay. Right, so those are the conjectures that I'm interested in. We now know the first one is false, and the other 3 are all still open. But I'll get to why the first one's false in due course. I think first, I probably owe it to you to make one little remark. Just justifying this assumption that we made, why the group has to be torsion-free. And it's a mild assumption, but it's something that we're imposing. The reason we're imposing is that it's very much essential. Otherwise, this is certainly all false, except for some very small number of cases. So this torsion-freeness is essential. So the most plain demonstration of this is that if I have some element G of order n, so G to the n is 1, and there's no smaller power of G that's trivial. So and I guess I'll also want this to be not G's the trivial element. So if something has order n at least 2, then I can just factorize 1 minus g to the n as follows. Very familiar factorization. Right, so this will be 1 minus g to the n, which is 0. So the moment I have torsion in the group, regardless of what the field is, there'll certainly be 0 divisors in the group ring. So for the other two, it's slightly different, but basically, except for some exceptions, the moment there's torsion, everything is completely false. But when there is torsion, who knows? It's very difficult to say. Okay. So, are there any questions at this point before I continue?
So it's very clear.
Okay. So these conjectures are all formally very similar. They all sort of look like they're saying roughly sort of similar flavored things, but they're actually also connected in a precise way, namely that there's this chain of implications. So this is valid for each group ring KG under the assumption that G is torsion-free. So if the unit conjecture holds for that group ring, then in fact the zero divisor conjecture also holds. I think it actually took quite a while for people to realize this. It uses work of Passman and Connell. So this implication is, I guess, not deep, but it also requires quite a bit of work, and this especially requires quite a bit of group theory to prove. So yeah, I taught a lecture course a year ago, and we did all the details of this proof, and it certainly filled a few hours. But then what isn't very difficult to prove is that if the zero divisor conjecture is true, then the idempotent conjecture is true. And the reason for this is just a simple contrapositive. So if the idempotent conjecture fails, and I have some non-trivial idempotent x, then, well, I can just sort of rewrite that equation as saying that x times x minus 1 is 0. And the assumption that x is a non-trivial idempotent is exactly the same thing as saying that none of these two factors is 0. So that's why I now have non-zero zero divisors. And finally, this direct finiteness conjecture is something that applies to all groups, but if I'm talking about a group that's also torsion-free, then it's a consequence of the idempotent conjecture, if the idempotent conjecture holds. Sorry, so, and the reason for that is also a very simple little ring theoretic observation, namely that if xy is 1 and yx, sorry, I'm out of practice with this way of writing, yx is not 1, then yx is our non-trivial idempotent. It's a non-trivial idempotent. Okay. Right, so those are the three implications. Two of them are very easy ring theoretic things, and they don't really have anything to do with groups. The first one requires a fair bit of group theory, and that's perhaps not so surprising because even stating the unit conjecture requires referring to groups. I mean, the zero divisor conjecture, the idempotent conjecture, the direct finiteness conjecture, these are all purely ring theoretic statements about the group ring, whereas the unit conjecture is something that only makes sense for group rings. There's no notion of what a trivial unit should be if I'm talking about an arbitrary ring. Okay. So those are how the conjectures relate to each other. And I think they're attractive conjectures to try and study, just because they're very fundamental questions we can ask about group rings. But they're also of interest because they're connected to other, if you like, more sophisticated conjectures, things which aren't just a simple first order statement about the ring in the way that I've stated them here. So one of these sophisticated conjectures is the Atiyah conjecture on the integrality of L2 Betti numbers. So this is something from global analysis. And I won't get into exactly what this says, but if you're familiar with the theory of L2 Betti numbers, then you've probably come across the Atiyah conjecture before, saying that they should be integral if we have a torsion-free group. And it's essentially, if you're familiar with this theory, then it's essentially a one-line exercise to see that if I'm working over the field of complex numbers, then the Atiyah conjecture being true immediately tells me that zero divisor conjecture is true. Otherwise, we'd have some operator from one-dimensional modulator von Neumann algebra to itself, whose kernel will have some von Neumann dimension strictly between 0 and 1. So the T conjecture is open for groups that are torsion-free, and it's maybe something that's difficult to get your hands on, but if you had a zero divisor over the complex numbers, this would be a very concrete way of seeing that the T conjecture can't possibly be true for that group. And some other sophisticated conjectures are some isomorphism conjectures from K-theory. So there's the Baum-Kohn conjecture in operator K-theory, and its cousin, the Farrell-Jones conjecture in algebra, for the algebraic K-theory of the group ring. And again, if either of these is true, for simplicity, let's just say we're working over the complex numbers, then the idempotent conjecture is true. Okay. So these are, again, conjectures which, for torsion-free groups are wide open. Some stronger or related versions of Baum-Kohn have been disproved, but for sort of plain basic Baum-Kohn, that conjecture is open. Okay. And finally, there's a notion of sophicity. So this is something that was introduced by Gromov and named by Benji Weiss. And so a group is sophic if it's approximated by finite groups in a very flexible sense. So the class of sophic groups includes amenable groups, residually finite groups, or more generally includes all residually amenable groups. And it's an open problem to show if any non-sophic group exists at all. If a group is sophic, then it has as a consequence that the group algebra or group ring is directly finite. So again, there's this sort of kind of complicated question which has a very concrete prediction for the group ring. So if you could find a group ring and that was not directly finite, then you'd have a very concrete proof that that group's not sophic. Okay. So those three conjectures are all related to these big mathematical machines. And for the unit conjecture, there's no big machine that we can feed a group into in order to prove that the unit conjecture is true. All we have is one very, very small custom tailor-made machine, which is called the unique product property. So this property that I'll now introduce is sort of, if you like, the property that you introduce to extract what's really going on in some pre-existing proofs of the unit conjecture. And ultimately, all proofs that we have of the unit conjecture for groups where it is known are a consequence of the group having this very combinatorially flavored property, which then yields the unit conjecture as sort of a more or less immediate consequence. Okay, any questions?
So what is the unique product property?
So that's what I want to introduce now.
Okay.
Yeah. Right. So this is definition 2 of 2 for the talk. So G is said to have the unique product property if whenever I take two non-empty finite subsets, A and B, then there's some product of an element from A and an element from B, which is unique amongst those products. So it has a unique product property if for all non-empty A and B, and these have to be finite inside the group G, there exists some U in G, the unique product, such that U is of the form A times B for a unique pair in the product. Okay, so it's one of these things that's fairly easy to define, but I know it's very confusing when you first see it to try and parse what's really what's really happening. So maybe the first observation is the remark that any group with this property is necessarily torsion-free. So only possible if G is torsion-free. Right? Because if G is not torsion-free, then I can find some finite subgroup H that's non-trivial. For example, pick any torsion element and consider the cyclic subgroup it generates. So if this is a subgroup of G that's finite, then we can just take both of these sets A and B to be H. So if H has got size n, then when I consider all n squared products, I'll just get the n elements of H, each occurring n times. So there certainly won't be any unique product. They're all occurring the same number of times. So this is something that is really only of interest for torsion-free groups, can only possibly happen for torsion-free groups. And another example would be this is true for say the integers, our running example, because if I have two non-empty finite subsets of the integers, I can just take the maximum of each, and their product, if I'm thinking in multiplicative notation, will be the unique one. So this holds for Z, and we can just take as the pair AB, the max of A and the max of B. So another way of seeing this is that if I take two non-zero polynomials, then I know their product is also non-zero. And the reason I know that is I can tell in advance exactly what the leading power of t will be, the highest power. It'll be the highest power of one plus the highest power of the other. Okay. So this thing that's happening with Z involves some sort of ordering, and this argument I was actually using the fact that Z is bi-ordered, so it has an ordering that's invariant for both multiplication on the left and the right. Okay, Z's abelian, so actually there's not really a distinction between left and right. But in general, this argument where we take the max of each of the two sets, that requires having a bi-ordering. But there's an easy fix that makes it work as long as we just have an ordering on the group that's invariant under multiplication on one side. If the group's left orderable, which is a much more general notion. So, sorry. Yeah. So to give you a bunch of examples, so key one is left orderable groups. So this includes many things: free groups, surface groups, torsion-free, nilpotent groups. I guess I'll just write some of these down. So torsion-free, nilpotent. And another very interesting example is the braid groups. Yeah, so a lot of people have been very interested in ordering braid groups, people like Thionois, Thurston, and so on. And a reason why the braid group example is particularly interesting is that there's one common way to prove that a lot of groups are left orderable, which is to show that they are locally indicable, meaning that all the finitely generated subgroups surject onto Z. So if I have a non-trivial finitely generated subgroup H of G, so for all non-trivial finitely generated subgroups H, there exists a surjection of H onto the integers. That's what locally indicable means, and if my group's locally indicable, then it's left orderable. But that's not all of the left orderable groups, and a very nice example of a group that's left orderable despite not being locally indicable is braid groups. So once we have at least 5 strands, then due to work of Goran and Lin, the commutator subgroup will be a finitely generated perfect subgroup. Okay. And slightly more general than left orderable groups, there's also a notion of diffuse groups that was introduced by Bowditch, sort of abstracting work of Thomas Delzon. But maybe I won't go into that. But this is a more geometric way of proving that this unique product property holds without appealing to having an ordering. Okay. So maybe I'll just leave it at that for the examples of left orderable groups. Right. So I sort of mentioned what happens with Z and why the zero divisor conjecture should be true for the Laurent polynomials, maybe, but what's actually going on in terms of the unique product property exactly. So I'll hopefully make this clear. So the observation is that if I have the unique product property, then the group certainly has the satisfies the zero divisor conjecture. So if G has the unique product property or has unique products, then whenever I take 2 non-zero elements of the group ring, I can take as these sets A and B the support sets of those elements. So the elements of the group for which the corresponding field coefficient is non-zero. So if you like, this is sort of a strict support. I'm not allowing any group element for which the field coefficient is 0. It has to be precisely those ones for which the field coefficient is non-zero. So I can then write my my first element is the sum over this set A, lambda G times G, where all of these lambda G's are non-zero. And similarly, I'll have a sum of H in B of, say, mu H times H. And when I evaluate this product, I know that I'll get, for this unique product U, I'll have this unique pair A and B. So the coefficient of U will just be lambda A times mu B. And I'm not adding anything else to this expression because it's a unique product. So the coefficient of U will certainly just be the product of these 2 non-zero things, and is therefore non-zero. And then we'll have a sum over all the pairs G and H where the product is not equal to U of the corresponding thing. But I don't really care what this sum is, because I know the group elements appearing here are all not U. So whatever this product is, I know it can't possibly be 0 because it has non-zero coefficient at U. So the conclusion is KG has no 0 divisors. And in fact, something stronger is true. KG has no non-trivial units. In fact, more strongly, the unit conjecture is true. Right, so the argument I just gave you is not enough to conclude that the unit conjecture is true, because maybe this unique product U is exactly the identity element of the group and everything else cancels. But there's a nice little argument due to Stranovsky, which shows that if you have this product, then whenever A and B are not both sets of size 1, they'll in fact be 2 unique products. There'll be some element U and some element U dash, each of which occurs in a unique way. So then I know if I have, I multiply 2 things in the group ring and they're not both trivial units, then the product certainly has non-zero field coefficient at least 2 different group elements. So it can't possibly be the identity of the group algebra of the group ring. Okay. Right, so if we want to disprove any of these Kaplansky conjectures about torsion-free groups, we certainly need groups that are torsion-free but don't have the unique product property. And it turns out that's surprisingly difficult to do. So there are a few examples in the literature. So these are examples of torsion-free non-unique product groups. So the way I see it, the groups sort of fit into 2 strands. There are 2 flavors of the groups. One uses some theory called small cancellation theory. Right, something in the realm of geometric group theory, where you produce these very large presentations where the relations have controlled overlap, and this lets you conclude that the corresponding group is torsion-free and that certain things are non-trivial in the group and so on and so forth. So this is first done by Rips and Segev in 87. So they sort of give you this recipe for producing some very, very complicated group that doesn't have the unique product property. And this sort of thread has been further developed by Marco Steinbock and his co-authors in various papers. So this one with Gruber and Martin, one with Argentseva, one just by himself, proving various things about ways that you can get non-unique product groups with certain additional properties. So this example of Rips and Segev showed that these things do really exist. I guess it had been asked maybe 15 years ago, 15 years prior to that, if such things exist at all. And it certainly settled this theoretical question, but I guess very difficult to work with concretely, because you end up with these very large presentations, like groups that aren't so amenable to actually doing explicit computations with. And that sort of brings me to the second strand of examples, the second flavor. And I'm going to give them a very non-technical term, and I'll just call them small presentation. So small cancellation is a theory that really means something. Small presentation is just some word I'm inventing here, which just means that it's a very concrete example of a group, and I can really write down a very small presentation of the group with a small number of generators and actually give you very explicitly sets that show that it doesn't have the unique product property. So shortly after Rips and Segev gave their example, Promislov showed that there's actually a very nice example of a virtually abelian group that doesn't have the unique product property. And then this was sort of generalized into a family of groups by Carter, and Lindsay Solberg in her master's thesis sort of studied very small ways that you can, very small finite sets that falsify this property, and in particular gave a very nice example of a virtually nilpotent group where you have 2 8-element sets that don't have a unique product. Okay, so what Promislov showed was that the easiest group we knew of that could have possibly been an example of a group without the unique product property really is a group without the unique product property. So what Promislov showed is that what I'll call the hunch event group So hunch and Venn studied the corresponding flat free manifold that this is the fundamental group of. So this is a group that sits in a short exact sequence. So it has a normal subgroup isomorphic to Z cubed. And the quotient by that subgroup is then just a Klein-Four group. So it's index 4 away from just being a free abelian group. So really very, very mild. And Promislov showed that it is not a UP group. But it is a torsion-free group. So in particular, this extension is not split. There's no Klein-Four subgroup of P. Right, and so I think Promislov was actually trying to understand why this group should have the unique product property and sort of accidentally prove the opposite of what he was trying to do. And he found some explicit 14-element set such that if you make A and B both this 14-element set, there's no unique product. Okay. And this is really the easiest example that could have possibly worked, because I'd argue that virtually abelian groups are the easiest examples of infinite groups. And in dimension 2, the only examples that are torsion-free are just Z squared and the fundamental group of the Klein bottle, which are both known to be unique product groups. And then in dimension 3, there's a finite list of them, and this is the only one that's not sort of obviously a unique product group. So it really was like the one easiest thing which it could have failed. And what I showed is not only does this fail to have the unique product property, it also fails to satisfy the unit conjecture. So what I showed, it's now already 4 years ago, is that if we take this group and take coefficients from the field with 2 elements, and this has non-trivial units. So after my work, someone called Alan Murray did a large computation to find an example with coefficients in the field with 3 elements, and then saw a clever way of extrapolating those 2 examples into a whole family that actually works for any characteristic P. So after that, the only remaining question was, well, what about characteristic 0, which is perhaps the most natural example, most natural question to ask, the most natural setting to study this. And in particular, it'd be very nice to give an example where the coefficients are actually integral. That's not something that I know how to do yet, but what I can do is algebraic integers. So then, at the end of 2023, I improved this to show that actually we can take the integers in cyclotomic field. So we just add an 8th degree of unity to the integers. That's my ring of coefficients. So yeah, of course I phrase everything in terms of fields, but I can consider this subring of the field of complex numbers, and that supports a non-trivial unit. But in fact, both of these examples are just the same 21 element set of the group. Okay. Now something slightly better than just having non-trivial units is true, which is that we have lots of units. So maybe I'll preface this corollary with a remark that if the unit conjecture is true, then we know exactly what the group of units is. I mean, we know all of the units and they form a group, and that group is then just the direct product of the units of the field and the group itself. It's pretty clear. There's a isomorphism here. And in particular, if the unit conjecture were true for this group P with coefficients from F2, then the group of units would be isomorphic to P. And so P being a very small group, for example, it's finitely generated and virtually abelian. So among other things, is also amenable, these properties would also be satisfied by the group of units. But even this sort of weaker version of the unit conjecture is false. So a corollary to my counterexample is that, in fact, there's not just one unit, there's tons of units, and they form a very large group of units. So the group of units is not finitely generated. And it's also very far from being virtually abelian or amenable or any of these things. It also contains free subgroups. Okay. Right, so unit conjecture fails for this group, very bad. There's lots of units. We still don't know what all of the units are. But one thing that seems to be true about the units, although it's not clear why this should be the case, it's just sort of an observation. So I had something related to this in my paper, but Laurent Bartholdi really gave a nice sort of coherent explanation of what the thing that I was observing is, which is that all the units we know exhibit some sort of symmetry that can be expressed in terms of automorphisms of the group ring. So Bartholdi observed all known units for this group are symmetric in the sense that they're invariant under some non-trivial group ring automorphism. And they're also what he called twisted unitary. I guess that's a good name for it. And right, so twisted unitary means it's something like being unitary, which would say if I take the star of this unit, so this star anti-involution for the group ring is just take each group element and replace it with its inverse. So if we were sort of proper unitary, that would mean that this thing sends the unit to its inverse, which is almost true, but there's this twist, namely there's some automorphism of the group ring that we then apply. So there's this relationship between the unit and its inverse, which is close to just being invert all of the elements one by one, but then there's also this twist that comes at the end. Okay. Right, so that's what we know about that group. That's not the only group we know to have non-trivial units. There's at least one more example. So this is another theorem of mine that we take the group that was studied by Solberg in her thesis that I mentioned before, which was a known example of a group without the unique product property, then that also has non-trivial units. Right, and this S stands for Solberg's group, which is very similar to the integral Heisenberg group. So for the integral Heisenberg group, I'd write the group generated by these two matrices. So Solberg's group is almost this, but we have these -1s coming in. So this group is commensurable with the Heisenberg group. It has an index 16 subgroup isomorphic to the Heisenberg group. It's important that it's not the Heisenberg group because the Heisenberg group is torsion-free nilpotent and therefore is left orderable, satisfies the unique product property and so on. Okay. Any questions at this point?
I have the questions. So you say the group P, so the P is defined uniquely by exact sequencing, because usually you can have many extensions, but so.
Right. So I guess it's probably not, it's maybe not even the unique torsion-free group that splits in that way, but it is a torsion-free group
you
that
say
splits in that way,
yeah.
and it's the unique one that is has first Betti number 0.
I see.
It's the only
So that is yeah.
the only one that's has finite abelianization.
Okay. So so that's the till now you have the only 2 group to play with, the group B and group S.
Yeah.
Yes.
So I think there should be many other examples, but yeah. I guess haven't focused too much effort on just giving more examples of groups. Guess I'd be more interested in giving an example with some group, probably these ones where the coefficients are integers. Yeah.
Yes, thank you.
Yeah, all right. Okay, so this non-trivial unit exists. It's some very complicated element of the group ring. It's the sum of 21 elements. Its inverse is also the sum of 21 elements. And the combinatorics of how these 441 products cancel in pairs to leave only the group identity, there's obviously like a fair bit of information there. It's difficult to find this thing by exhaustive enumeration. So the key idea in my approach that let me produce this unit was to translate the problem into Boolean satisfiability. Right, so the Boolean satisfiability problem, or SAT, is the oldest example of an NP-complete problem, and it's just you're given a Boolean formula, and you have to decide, can I assign the variables to true or false such that formula evaluates the true, so that it's satisfied. And of course, it's NP-complete, so you can't solve it quickly all the time, but it turns out that a lot of instances that you want to solve in practice are not as hard as maybe you would think. So I like to think that a SAT solver can the SAT solver, which is the software that's developed to answer this question as quickly as possible, it's able to surpass some sort of superficial difficulty. The problem looks hard because there's lots of variables and it's difficult to understand how everything's connected, but the SAT solver can very quickly either find some very short argument for why, I mean, short is relative, I guess, but can quickly find some argument for why there's no satisfying assignment, or it can give you the satisfying assignment. So of course, here we're just turning arithmetic over F2 into Boolean logic in that sort of obvious identification that 0 is false, 1 is true. The addition in the field is exclusive Boolean OR, multiplication in the field is Boolean AND. And so we just end up with some very large Boolean formula. We feed this into the SAT solver in some way, and then it can find the answer. So in particular, the SAT solver can find this unit because it's very sensitive to how exactly you phrase the question and so on and so forth. But I can say, I'd say roughly that the search space is something like, I mean, I'd say it's certainly something like 10 to the 30 in size at least. Maybe a sort of more naive way to think about it is probably natural to look in a search space of size 10 to the 44. Maybe if you're a bit more clever, the search space looks more like 10 to the 30, but at any rate, this is a really huge search space, right? The CPU on a computer runs on the order of gigahertz, so that means doing something like 10 to the 9 things per second. So really trying to exhaustively check through 10 to the 30 things is sort of not really possible, but the SAT solver can find it in some number of minutes. Okay. Right, and of course, the SAT solver is a completely general purpose tool. It can answer NP problems, NP-complete problems, NP problems that you reduce to SAT, and there's really like no restrictions on that. And of course, it's also a very natural tool to try and use for these other conjectures and various related questions about the group, like You can ask things like, does my group have a unique product property? Is it left orderable? And so on. And those things are also things that we can use SAT to attack. So, if it's just sitting there and it's a general purpose tool, why is the zero divisor conjecture still open? Well, of course, it's not just something that's formally going to be more difficult to prove. It's, I think, in practice, much more difficult to prove because there's a lot more groups for which the zero divisor conjecture is known to be true. So, for example, this group P, it satisfies the zero divisor conjecture. That's been known since, I guess, the early 80s or late 70s. So we need more complicated groups in order to be able to produce zero divisors. And in fact, if we look at these examples of non-UP groups I mentioned before, these small cancellation ones are not really feasible to work with on a computer, and these small presentation ones that are in the literature all satisfy the zero divisor conjecture. But I know there's at least one example of a group that doesn't have the unique product property and for which all techniques we have to prove the zero divisor conjecture at the moment don't apply. So certainly, the set of candidate groups is not empty, but I can't really say much more than that for now. So yeah, but maybe to just end with a little observation and something that I think is cause for optimism in a way. So if we think back to this diagram, there was this sort of, the strongest conjecture was the unit conjecture, and it was maybe the odd one out because it was something that only makes sense for group rings. Its relation with the others was somehow more complicated, and all the other conjectures were consequences of sophisticated things, and the unit conjecture is not really the consequence of any mathematical machine we have. So given that, we'd probably say the unit conjecture and the zero divisor conjecture are actually very far apart. But I'd argue that they're maybe not as far apart as they seem because of a small little observation, which is that G satisfies the zero divisor conjecture for all fields K. If and only if the group of units of the group ring KG, right, so if the unit conjecture is true, that thing's just units of K times G. In general, there'll always be this subgroup, normal subgroup isomorphic to the units of K. I can always quotient that out. So if the unit conjecture is true, this thing is just isomorphic to G. In general, the unit conjecture could be false, and then this will be some bigger group. But the zero divisor conjecture is actually equivalent to saying that this thing is torsion-free for all K. So the reason I'm making this remark is just to say the zero divisor conjecture can be seen as a statement about the units of the group ring. Okay, it's not saying they're all trivial, but it's saying the group of all the units is torsion-free. So for that reason, I think that maybe the zero divisor conjecture is not that different from the unit conjecture, and maybe there's hope that at some point we'll have counterexamples to that conjecture as well. I'll finish there.
Thank you very much. Yes. Yes. Thank you very much for very nice talk. Yes. Is there some more questions? So the monkey innovation is you translated the problem into Boolean satisfiability. So you use a SAT solver. So, but the problem of zero divisor, then you cannot how to say each problem in algebra. You can translate it using in some combinatorial problem and using a SAT solver. You don't know.
Yeah, I guess sort of any problem that has a very discrete combinatorial flavor that involves making some large but finite number of choices, and then something, of course, it has to be something that's in NP. It has to be a problem where if you're given a solution, you can then quickly verify it. yeah, of course, there's a big difference between sort of knowing in theory my problem is in NP, so there is some reduction to SAT, and actually having a reduction to SAT. And it can be a bit of a challenge to take your problem and reformulate it purely as a something in propositional logic, but with a little bit of determination, it's quite amazing what you can do.
So that's you have some theorem that there are only possible finite number of units, therefore you can apply such solver.
Sorry, could you repeat that?
You have the theorem of facts that there are only finite number of the possible unit, and then you can apply some algorithms, such solver, to find them.
Yes, yeah. Sorry, so something I guess I didn't really touch on at all, but yeah, the approach is to then exhaust the group by finite subsets, and then on each finite subset you can ask, is there a non-trivial unit whose inverse is also supported on this finite subset?
Yeah.
And of course, there's then different ways for how you could exhaust the group by finite subsets. I'd say the most natural way is to take larger and larger balls in the Cayley graph. So you're just picking some generating set and asking which words are a product of at most n of these generators and their inverses. Yeah, and if you do that sort of exhaustion, then that's where this sort of 10 to the 44 I mentioned came from. At some point, you have some, the smallest ball that works is the ball of radius 5 with these two generators. There's two natural generators for this group. And then you've got, I think, 147 elements. So then there's 2 to the 147 possibilities for what your unit could be.
Thank you very much. If there are no more questions, let us thank the speaker again, yeah?